Did you know Kth Smallest Element in a BST is a Pattern Mastery 100 essential and a go-to question at Google, Facebook, and Amazon to test your mastery of binary search tree properties and tree traversal? Over 30% of candidates stumble on this, either by missing the in-order pattern or handling K incorrectly. Nail this problem, and you'll be ready for everything from ranking queries to real-time analytics. Let's use the basic framework to tackle Kth Smallest Element in a BST step by step, so you'll be confident and clear in every interview. Let's break it down. Given the root of a binary search tree, BST, and an integer k, find the Kth smallest value, one indexed, in the tree. Input: root node of a BST, integer k. Output: integer value of the Kth smallest element. Here is a real-world example. Imagine managing a leaderboard where you need to find the Kth top performer. Or, in a scheduling app, finding the Kth earliest event among time slots stored in a BST. An interviewer might ask, how would you efficiently find the median or percentile rank in a huge, dynamically changing dataset? Let's assess. What's tricky? A BST's in-order traversal, left root right, produces sorted values. The challenge is to traverse efficiently and stop exactly at the Kth value. Think step by step. Perform an in-order traversal of the BST. Use a counter to keep track of how many nodes you've visited. Once the counter reaches k, record the node's value and stop. Be careful. Do not keep traversing after finding the Kth node. Let's clarify. You can do this recursively or iteratively, using a stack. If the tree is very large and k is small, the traversal short circuits early. Edge cases. K is 1, smallest, k is tree size, largest. Here is the structure. Initialize a counter, starting at 0, and a variable to store the result. Traverse the tree in an order, left root right. At each node, increment the counter. If counter equals k, record the node's value and return immediately. Return the result. Now let's implement the in-order traversal method, leveraging the BST sorted property to retrieve the Kth smallest element. We begin by defining a solution class. This just organizes our method neatly. This function will return the Kth smallest value in a binary search tree. Thanks to BST properties, an in-order traversal gives us values in sorted order. Time complexity, O(n) in the worst case. We create an empty stack list. This will help us perform a manual in-order traversal, going left as far as possible before stepping back. We set a pointer node to the root so we can walk through the tree. We'll use count to track how many nodes we visited in sorted order. Once count hits k, we found the answer. This loop keeps running as long as we still have nodes to explore, or we have nodes stored in the stack. This ensures we traverse the entire left root right order. When we see a node, we always go left first, just like reading a sorted list from smallest to biggest. We push the current node onto the stack. Think of this like dropping breadcrumbs so we can return after exploring the left child. Then we move left. And we keep doing this until we can't go further, reaching the leftmost node. When the left path ends, we pop from the stack. This gives us the next smallest node in the entire tree. We've officially visited one more node in sorted order, so we increase our count by 1. We check if this is the Kth node we visited. If it is, we found the answer. We return the node's value, the Kth smallest element in the BST. If this wasn't the Kth node, we move right and continue the in-order traversal. This keeps the sorted order going. And that's how this algorithm works. It first sets up a stack and pointer, then in order walks the BST, counting nodes until it lands on the Kth one. Efficient, simple, and elegant. Let's test our in-order-based solution using this tree. 3, 1, 4, null, 2, with k equals 1. This represents a binary search tree where 3 is the root, 1 is the left child of 3, 4 is the right child of 3, 2 is the right child of 1. Because it's a BST, an in-order traversal, left root right, we'll visit the nodes in sorted order, performing in-order traversal. Go left from 3 visit subtree rooted at 1. Left of 1 is null, so we visit 1. Then go right to 2 visit 2. Then visit root 3. Then visit right child 4. So the in-order sequence becomes 1, 2, 3, 4. Now, k equals 1, which means we're looking for the first smallest element in the BST. In this sorted list, the first element is clearly 1. That's our answer. And that's exactly what our function returns, 1, which matches the expected result. So, our implementation is correct. The in-order traversal collects the nodes in sorted order and picks the Kth element precisely, giving us the correct smallest value. Now let's implement the min-heap approach, collecting values and extracting the Kth smallest using heap operations. We start by importing Python's heap.epe module. This gives us a min heap, a data structure that always keeps the smallest element at the top. We define our solution class, which simply organizes our method. This method will find the Kth smallest value in the binary search tree. Unlike the inorder approach, this solution collects all values and uses a heap. Time complexity, on plus k log n. Because pushing all nodes is on, and popping k times from a heap costs k log n. We initialize an empty list called heap. This will become our min heap of all node values. We define a helper function traverse to walk through the whole tree. This will push every node's value into the heap. This is our base case. If we hit a null node, we stop exploring that branch. Here we push the current node's value into the min heap. The heap automatically keeps the smallest values at the top, like sorting, but done progressively. We move to the left child and continue the traversal. Then we explore the right child. Overall, this step gathers all values from the BST. We kick off the traversal starting from the root. After this line finishes, the heap contains every value in the tree. We now pop the smallest values from the heap until we reach the Kth1. We pop k1 times, leaving the Kth smallest at the top. This removes one element from the heap. Each pop gives us the next smallest value. This happens k1 times. And finally, the next pop gives us exactly the Kth smallest value. That's our answer. And that's how this algorithm works. It first collects all values in a minute heap, then removes the smallest values until the Kth1 surfaces. Efficient, simple, and elegant. Now we'll test the min heap approach with this input tree. 5, 3, 6, 2. This tree represents a BST where 5 is the root, 3 is the left child, 6 is the right child. Under 3, 2, left, and 4, right under 2, 1, left child, the goal is to find the third smallest value in this BST. With the min heap strategy, we traverse the tree and push all node values into a min heap. The heap automatically keeps the smallest element at the top. We then pop from the heap k times. The element we get on the Kth pop is the Kth smallest value. If we look at the BST values in sorted order, they are 1, 2, 3, 4, 5, 6 first smallest 1, second smallest 2, third smallest 3. So after popping 3 times from the min heap, we should end up with 3. And that's exactly what our program outputs, 3, matching the expected answer. So, our implementation is correct. The min heap approach successfully pulls out the Kth smallest value, and even though it's slightly heavier than pure inorder when you just need k, it still works efficiently and accurately for this test case. Finding the Kth smallest element in a BST is one of those problems that looks simple, until you realize how much it reveals about your grasp of tree structure and traversal. This one tests whether you truly understand how BST ordering naturally connects to inorder traversal. Let's do a recap. Conceptually, the problem is about ranking within a tree. We're given a BST and a number k, and we need the Kth smallest value. Because a BST's inorder traversal visits nodes in sorted order, our goal becomes traverse in order, and stop at the Kth step. The key insight here is that you don't need to sort anything manually. The BST structure does that for you. The challenge is controlling traversal flow and counting visits correctly. Whether you choose recursion or a stack-based approach, stopping at exactly the right moment is what keeps the solution efficient. We built the plan like this. Start an in-order traversal, move left first, visit the node, then move right. Keep a running counter of visited nodes. When the counter equals k, capture that value and stop traversing. That's the entire sorted order distilled into one clean recursive flow. We implemented that logic using either recursion or an iterative stack. Each node visit increased the count, and when the count matched k, we returned the node's value immediately. No unnecessary traversal or extra data structures were needed. Testing on LeetCode confirmed the method's precision. For k equals 3, the traversal sequence 1, 2, 3, 4, 5, 6 correctly returned 3. Edge cases, like k equals 1 or k equals number of nodes, also worked flawlessly, proving the counter logic and traversal control were solid. The big takeaway? The inorder traversal is your built-in sorted list for BSTs. By combining it with precise counting, you can extract ranked elements directly from structure. No sorting, no arrays, just pure logic.